Our next lesson in the mole unit is on empirical formulas. Here you can see the learning targets for our unit. We want to start by simply giving some definitions. Two definitions we want to be familiar with. The first is an empirical formula. An empirical formula is the simplest whole number ratio of atoms of elements in a compound. We will contrast this with a molecular formula, which is the actual number of atoms of elements in one molecule of a compound. So these are some definitions you want to be familiar with. Now let's take a look at how those definitions apply to each other. What we should be able to do is determine an empirical formula of a compound if we're given its molecular formula. So let's look at some examples. So we're just simply asked to determine the empirical formula for each compound. So let's say we're given the molecular formula H2O2. That's hydrogen peroxide. And what that tells us is in one molecule of hydrogen peroxide there are two hydrogen atoms and one oxygen atom. Now the empirical formula is just the simplest ratio of those. Well, if there's two atoms of each, the simplest ratio, or the empirical formula, would be 1 to 1. So our empirical formula is simply HO. Let's look at another one. Molecular formula C4H10. That would be butane. Now ask yourself, what can I divide both of these numbers by and still make these whole numbers? Well, I can divide them both by 2. If I divide them both by 2, that would give us C2H5. That would be the empirical formula, or the simplest whole number ratio of the atoms in that compound. Here's another example, C6H18O3. Each of these could be divided by the number 3. If I divide them all by 3, that gives us C2H6O, or the empirical formula. And then finally we have the molecular formula H2O. You might recognize that as being water, and it is. Now here the empirical formula is actually the same as the molecular formula, because this is already the simplest whole number ratio, so it's not going to get any simpler. So the empirical formula would just be H2O. So if we're given the molecular formula, we find the empirical formula just by dividing by what would be the greatest common factor of those number of atoms. Now these next two learning targets really go together. We want to be able to determine an empirical formula of a compound from percent composition data, and we also want to determine a molecular formula of a compound once we have its empirical formula and its molar mass. I have a couple of examples for us to look at here, but before we do the examples, there's a list of steps that I want to show you. Anytime we are finding an empirical formula from percent composition, we'll want to follow the same steps. It's not too often I can give you a list of steps to follow for a particular problem, but this is an exception to that. The first step we want to follow is we want to convert the masses of the elements in the compound to moles. Then we'll obtain the mole ratios of those elements by dividing each by the smallest number of moles. If necessary, we'll then multiply that ratio to make only whole numbers. And then we'll write the empirical formula. So as far as finding the empirical formula, that's the end of it. If we're also asked to find the molecular formula, there's one more step we need to do. And that's simply following an equation. A molecular formula would equal the empirical formula for the compound times the ratio of the molar mass over the empirical mass. Now, we'll see some examples of all these steps in action here, so don't feel like just after watching this one slide you should have this down. These next two examples will go through each of these steps for you. Alright, so let's just take a look at an example. Here's a problem. A compound is 73.14% carbon, 7.37% hydrogen, and the rest is oxygen. The molar mass of the compound is 164.2 grams per mole, and we're asked to determine the empirical and molecular formulas for the compound. So what we're given here is percent composition data. Remember, these percent compositions are percent by mass. So if I had 100 grams of the compound, 73.14 grams would be carbon, 7.37 grams would be hydrogen, and the rest of it would be oxygen. So our first step is we want to convert the masses of the elements to moles. If we're not given masses, as in this case, we're given percent composition data, all we need to do is change these percentages directly into masses, because we know per 100 there would be that many grams of each of those elements. So for example, in this case, we're going to convert 73.14 grams of carbon, notice that matches the percentage, we're going to convert that to moles. To do that, we would just use the molar mass of carbon, just 12.01, use that as a conversion factor, and you convert that into moles. In this case, you would get 6.090. And you would just do that for all the elements in the compound. 7.37 grams of hydrogen, convert that into moles, again use the molar mass, that would give you 7.30. And then for oxygen, notice I get my oxygen, the 19.49 grams. That would be the difference between 100 and what we already have, the 73.14 and the 7.37. That's how I get my 19.49. Convert that into moles, and that gives us 1.218 moles of oxygen. So there's the first step. We've converted masses into moles. This particular step is nothing new. We've done these mole and mass conversions before, so it shouldn't be anything too difficult for you there. Second step, we want to obtain the mole ratios by dividing by the smallest number of moles. So here are the mole calculations, the answers to those we just got from the last step. Notice I've just written them out here in a ratio using a colon here, common way in math to show ratios. I'm going to divide them all by the smallest number, and here's why we do that. There's really two reasons for it. First of all, if you think about writing formulas, we never write formulas with fractions. C 6.09, H 7.3. We need whole numbers. Second of all, the reason we want to divide by the smallest one is that ensures that the smallest number we're going to get is 1. We never write a formula with a subscript less than the number 1. So if we divide by the smallest, that ensures that that is the smallest number we could get. So I'm just dividing each of these number of moles by the smallest number of moles, which in this case happens to be 1.218. When you do that, you're going to get 5 moles of carbon, 6 moles of hydrogen, and 1 mole of oxygen. Now, when you actually plug this in your calculator, you may or may not get exactly 5 or exactly 6. In fact, in a lot of situations, you probably won't get exactly 5. You might get 4.998 or 6.0027, something along these lines. The only reason they don't come out to exactly whole numbers when they're supposed to be, as they are in this case, is due to measurement error and rounding from this initial data collection of these percent compositions that we're starting with. You have to use some intuition when you plug this in your calculator. If it's really, really, really close to a whole number, it probably is that whole number. It's probably, in this case, 5 and 6. Now, if you have a situation where it's, say, 5.2 or 4.75 or 4.33, then you wouldn't simply round to the nearest whole number. We'll see an example of that here in a second, what we would do with that. All right, so there's step 2, or B. We've obtained our mole ratios by dividing by the smallest number of moles. Next step, if necessary, we'd multiply this ratio to make all whole numbers. Notice these are already whole numbers. When we did the division, they came out to whole numbers, so there's nothing to do there. So not necessary for this example. Step D, we're just going to write the empirical formula. Here's the ratio we have. So our empirical formula is C5H6O. Here are 5 atoms of carbon for every 6 atoms of hydrogen for every 1 atom of oxygen in this compound. Or 5 moles of carbon for every 6 moles of hydrogen for every 1 mole of oxygen. Either way you want to look at it. So we've done the empirical formula. So the first part of this problem has been completed. Now notice we're also asked to determine the molecular formula. So here's how we do that. Here's the equation we're going to use. We are going to find the ratio of the molar mass to the empirical mass. Notice in the problem we're given the molar mass of the compound. We're told up here the molar mass of the compound is 164.2 grams per mole. That would always have to be given to you. You could not calculate what the molar mass is because you don't know the molecular formula of the compound yet. So you'd have to be given that. The empirical mass, that is simply the molar mass of the empirical formula. That's all that is. So our empirical formula from before is C5H6O. So we just want to calculate the molar mass of that formula there. And if you do that, that would give you 82.11. Now we're going to find this ratio of the molar mass divided by the empirical mass. So I'm going to take my molar mass, which is given to me, 164.2 grams per mole. I'm going to divide it by my empirical mass. And in this case, I get 2. Now when you plug this in your calculator, it's not going to be exactly 2. Looks like this would be 1.999, something along those lines. But it has to be a whole number or something really, really, really close to it. The only reason it doesn't come out to exactly a whole number, again, is due to measurement error and rounding that you've had from before. If you plug this in your calculator and you get 2.3, or you get 9.7, or you get 6.85, something along these lines, you can't just round it to a whole number. It has to be a whole number. If you do this calculation and you get a number that's not a whole number, what is the most likely source of error is that your empirical formula is not right. So you'd want to go back and check all that process, that calculation, make sure you have it right. The reason this has to be a whole number is because of the nature of what an empirical formula is. This formula is it is the simplest ratio of the molecular formula. In other words, the molecular formula is going to have this same ratio of atoms just multiplied by some whole number. That's why this ratio here has to be a whole number. The fact that this is 2 tells us there's twice as many atoms in the molecular formula as there is in the empirical formula. So all we're going to do is we're just going to take our empirical formula, the C5H6O, multiply all the atoms by 2. So that gives us C10H12O2. So in this particular compound, in one molecule, there'd be 10 atoms of carbon, 12 atoms of hydrogen, 2 atoms of oxygen. That's the molecular formula. All right, let's look at a different problem. Same question, but just a different compound here. We're told a compound is made of 88.17% carbon and 11.83% hydrogen. Again, we're given the molar mass. You can see that there. And again, we're asked to find its empirical and molecular formulas. So this is the same process we just used. So the first step, we want to convert our masses of the elements to moles. So converting our mass of carbon into moles, again just using the molar mass, that gives you 7.341 moles of carbon. And then for hydrogen, that gives you 11.74 moles of hydrogen. So there's the first step. Second step, we want to find our mole ratios by dividing by the smallest number of moles. So again, the reason we divide by the smallest number is to ensure we get a number no smaller than 1. This is going to give you 1 mole of carbon to 1.6 moles of hydrogen. Notice this isn't a whole number like we had in the last example. Now, when you plug this in your calculator, it's probably not going to be exactly 1.6, maybe 1.597 something or 1.603. I don't have the answer right in front of me here. But you have to use some intuition here. Ask yourself, what is the simplest fraction or decimal that could be? It's really, really close to 1.6. That's probably the case. If you think fractions, that would be 3/5 would be 1.6 or 1 3/5 is what that would be. So our ratio is 1 mole of carbon to 1.6 moles of hydrogen. Next step, if necessary, multiply this ratio to make only whole numbers. Well, it is necessary here because you'll notice we don't have whole numbers here. So we need to ask ourselves, what number can I multiply this ratio by to make both of those numbers whole numbers? The easiest way to think about this is to look at your fraction or decimal. It's probably easiest to think about it in fraction. 1.6 would be 1 3/5, where the denominator in that fraction is 5. So if I multiply this whole ratio by the number 5, that's what I'm going to do here, then I'm going to make everything a whole number. 1 mole of carbon times 5 would be 5 moles of carbon. 1.6 moles of hydrogen times 5 would be 8 moles of hydrogen. So my ratio is 5 moles of carbon to 8 moles of hydrogen. As far as the empirical formula is concerned, now we just need to write it. From before, our ratio is 5 moles of carbon to 8 moles of hydrogen. So the empirical formula is C5H8. So there's the empirical formula. Last thing we need to do here is to find the molecular formula. Again, we're going to find the ratio of the molar mass to the empirical mass. So the empirical formula from before is C5H8. Remember, the empirical mass is just the molar mass of that empirical formula. So find the molar mass of that. That is 68.12 grams per mole. The ratio of the molar mass to the empirical mass is 1. 68.11 divided by 68.12. Again, your calculator is not going to tell you exactly 1. but it's going to be really, really close to 1. So much so that that's what it is. If there was no measurement error, no rounding error, it would be exactly 1. So what that tells us is the molecular formula is the same as the empirical formula. There are the same number of atoms in the molecular formula as there are in the empirical. So our molecular formula is simply C5H8. Alright, that's the last example here. So these last 2 learning targets, we saw a couple of examples. Work on remembering the steps. The big idea is simply remember you're looking for mole ratios. If you can remember that, that tells you have to convert masses to moles. There's going to be some sort of division in there to find a ratio, and then know that they have to be whole numbers. If you can do that, then most of these calculations are pretty straightforward for you.